So now should I wait that everybody's in, or? Okay. So when so in fact, Jan's paper, Invention's paper, contains many things. I mean, it contains a proof of rationality of the Serre series, but it also shows that one can avoid using McIntyre's result. One can avoid using resolution with some further work. And for people from number theory who were not so much aware of model theory, it was not so satisfactory because McIntyre's proof was quite, in spirit, it was a model theory proof. So then sometimes later, Jans gave a proof of McIntyre theorem by using a cell decomposition. And in fact, the cell decomposition is more or less equivalent to McIntyre's theorem. And he gave for which he gave a direct geometric proof. So with that result, I mean, there was a proof of rationality, avoiding model theory. But what I want to stress is not that one can avoid model theory, is that in fact this cell decomposition theorem showed to be a very efficient tool to prove interesting results about integrals. So the cell decomposition is in my notes. It's a bit technical. It's nice, so I will not write it on the blackboard. What I want to mention is the behavior of volumes or integrals in a definable family. So using cell decomposition, Deneuve proves the following result. So you take a set with parameters. So some parameters in QP, some parameters in Z. So you suppose this is a definable family, say, of bounded subsets of some other QP to some power, say, n. Then you may want to consider its volume with respect to the parameters. And it is a very special function. It's a finite Q-linear combination of functions of a certain type. So p to some power. So the parameters are lambda and L, or beta, alpha and beta are definable functions with values in Z. So that's the theorem. And in fact, it's more general. I mean, you can take a so in fact, you can consider this kind of functions, and you can integrate them in a family, and you still get a function of the same time. So you have a certain algebra of functions, that is stable under integration. And this gives when you have this statement, you have a nice conceptual proof of rationality theorem. So assume no L, no lambda, sorry, here. So this means that your family only depends on L in Z to some power. So then E of L is a finite, or I don't need to write it, but you get alpha and beta. They are what they are? They are just Presburger functions. Then you deduce the following corollary.
What's I sub L?
I'm sorry?
I sub L. Here, then I sub L. What the other
Oh, then it's
Then alpha beta.
yes,
Alpha
it's
beta, right,
okay. So one deduce says the following corollary, that the notation was badly chosen here. I mean, it should be some error. So I of L is very simple functions. I mean, it's a linear combination of function of Presburger functions and exponential of Presburger functions. These Presburger functions, they are very simple. I mean, you have nice partitions where they are just linear. And so it's very easy to prove that this series is rational, always. And you have a corollary of the corollary is that P and Q. Oh, I'm sorry. And then you get as a corollary a proof of rationality of Q and P. Maybe to get this as a corollary, you need to have the version with where you integrate functions instead of just volumes. This is a stupid question, I'm sorry, but when there is no lambda, a sub lambda L is just S sub L.
Oh, I see.
So I wanted just to stress the importance of cell decomposition to prove a general structure theorem like that. Okay. Now we will go to the direction of Motivic integration. But we will not go there directly. I will give another type of applications of p-adic integration, quite unsuspected application, is how to use p-adic integration to prove results over the complex numbers. So maybe a few minutes of philosophical comments. In some sense, maybe it's not so surprising that one can do such a thing. Because in some sense, it's just another level of Axe approach to proving that injective polynomial morphism are isomorphism. So Axe used counting over finite fields to prove certain results over C. And something I should have said is that in some sense, not in some sense, but really p-adic integration is a version of just counting points over fq, but I mean, now it's qp is infinite, but you have reduction mod powers of p, and there you can count, and integration is related to counting modulo p to the n and passing to the limit. So for qp, you have integration. Replaces counting. Now I take f, a complex polynomial. I am not stating things in the greatest generality, but and consider so I will slightly change notation. Before x was here, but so this is just x is just the affine space of a C in n variables. Now I'm doing algebraic geometry. Okay. So assume y is smooth. H is proper, birational. Isomorphism outside the pre-image of f equals 0. And that this is a divisor with normal crossing, which means the following. As a divisor, so ni's are just numbers. Ei is just smooth. A divisor on a smooth variety is just another name for an hypersurface. And the Ei's, they intersect transversely. So the existence of such an H comes from Hironaka. So now I need some notation. I take any subset I of J. I will consider the intersection of the divisors corresponding to this subset. And I will also throw away the other components. So Y is just the disjoint union of all the. There is some stupid trick here that one should consider this part, which is just the complement of the pre-image of the hypersurface. Okay, we are almost done. So we consider the pre-image of differential forms on X. This is the sheaf of differential forms. And as a divisor, it's the same as the one on Y, but there is a correction term on the EIs. So in terms of local coordinates, I'm afraid there is it's up to 1. New I guess is maybe mi plus 1. Oh, what's the here I is j? Is what you mean? What's the problem?
No, the multiplicity.
No, it's not the ni. I mean,
Oh, it's not.
Ni minus.
Ni minus 1.
no, they have nothing to do.
Oh, oh sure. Yeah.
I'm defining some other numbers
Yeah,
here.
yeah, for sure.
Okay.
Good, yeah, I got it. Yeah.
But you remember that in the p-adic case, I defined some small mi's in.
All right.
And in fact, that's the same as new i's up to 1. Okay? So this means that locally, So I'm in dimension n, yes, okay. Yeah, it's a unit times. Okay, so they're the same as writing this formula. So now I can state the following theorem. And so I think it was published in 92, but it's in fact it was proved at least in 87, I think, maybe yes. Okay, so it's quite old. That so I have taken certain morphism H from Y to X, and so I have all this data. I will explain what I mean with E. So the statement is that the right-hand side is independent of any choice I could have made. So it depends only on the equation F, and so I name it that way. So everything here is clear except what is this Euler thing. So the Euler characteristic, Euler number of W for W complex algebraic variety, I will just define it as the alternating sum of the rank of the cohomology group with compact supports of the point of WC. So it has a fundamental additivity property that so it's a well-known Euler characteristic of X. Okay. Now I explain the proof of the theorem. So I should say that now the theorem has other proofs. So I will present the proof by p-adic integration. Later on, it will become obvious with using Motivic integration. But also, a few years ago, I think I will mention this theorem next time, more precisely maybe. There is a weak factorization theorem of Abramovich, Karu, Matsuki, and Wlodarczyk. It's a very hard theorem that gives a very precise very simple models for birational morphism. So if one uses this very strong result, then one gets for free, almost, that this is independent of the resolution. But this is more recent than this approach, and this approach will show you more or less the prehistory of Motivic integration. And the Motivic integration approach will anyhow be more interesting because it will not only prove that the right-hand side is independent of any choice, but it will give an a priori definition of the left-hand side. I mean, it's better to know a definition of some object than to know that it's independent of the choices. Okay, so in fact, at the time, this theorem was considered by Jan and me as a complete failure. I mean, because our aim was not to prove this theorem, but to do something else. I will explain. But we started with p-adic integrals, so a sketch of proof. So I will begin by cheating completely. I will assume that f has coefficient in the number field.
Does this have to be an affine hypersurface, or does it work?
Oh, no, I mean, this was just for simplicity. I mean, any divisor in a smooth ambient space. So so, of course, some work is required to pass from general case to this one. It's not exactly what we do, but okay. And consider P a prime ideal. Okay, P the corresponding conclusion. And we consider the corresponding p-adic integral. Okay, the one that appeared in Iguza's proof, and that nowadays is known under the name of Iguza local zeta function. Take the morphism H to be defined over K, and also the EIs and everything. Then there is a result of Jan that expresses this integral in terms of the geometry. And the formula is close to the one here. Oh, the formula is not that one. I mean, I don't remember. I should look to my notes. Okay, that's the formula. So I should explain what. So Kp is the residue field. Of capital Kp. So I should explain what I mean by this number. So my EI with a circle on the top is a variety over K. So what do I mean by its number of points in the residue field? So I can choose the model. It means the equation defined over the ring of integers by throwing away denominators. And I can look to reductions mod P. And of course, this will depend on the choice of a model. But at least for almost all P, it will make sense. So this makes sense for almost all P. And what is the Q? Q is a number of, is a cardinality of the residue field. So now the idea is to take Q going to 1. If Q goes to 1, this goes to 1, okay? This is quite clear. I mean, it goes to this term, which the one is the one I'm interested to when Q goes to 1. So when I take Q going to 1, I obtain something looking similar to the right-hand side there. Except that, of course, I should make sense of this going to 1. Now take W variety over my global field K. So as I explained, I can consider its number of points modulo the finite residue field for almost all P. But the whole point that this has a cohomological formula. It's a trace of the Frobenius on some cohomology group of W. Okay. So I don't want to explain what is written here, but this has the effect that it can be written in a certain way. So the trace of an operator is just the sum of these eigenvalues.
W smooth?
No, but it has nothing to do with smoothness. So you have something like that. That's fine, but one does not see how it helps to taking the limit. So now the key idea is taking finite extensions. So we denote by so we take the finite extension of degree E of the finite field, and the corresponding unramified extension of degree E. So now the whole point is that you can consider also the integral over the ramified extension. And the formula of Denef holds for all E. I mean, for almost all P and for all E. And then you replace Q to the power Q to the E here. This. Here minus E. Okay. And now instead of taking the limit of Q, we will take the limit of E goes to 0. And now what happens when it takes the extension? The point that the Frobenius is given by the iterate of the Frobenius. So the eigenvalue are just the corresponding powers. But that's nice because now when I do E equals 0, I get 1. So I just count the number of eigenvalues, which means just counting ranks. So one gets that for almost all P, limit when E goes to 0 is the Euler number of WC, of W. So there is, of course, I'm going very fast because here when there's some other kind of cohomology, l-adic cohomology, so one needs to have some comparison results which hold. And also, I'm cheating a lot because this is nonsense because E is, of course, just a natural number. So what's the meaning of taking a limit when E goes to 0? But OK, this can be done. I mean, this is a very special function of E, so one can define its limit as E goes to 0 and so on. And now one takes the limit when E goes to 0. And one gets the theorem. So remark, so it's the same as morally. We did integration on the we were just taking Q going to 1 or P going to 1, so it was just the field with one element and its vector. Of course, this has no meaning. But
does this mean that when E is some logarithmic, like
yeah, one should be careful. I mean, but it's not hard to give
I
meaning
would
to.
actually agree. Like when we sort of, if I fix P to be some prime, and as E is moving, and
Yes.
P to the power of E turns out to be another prime. Will those two
The question is the result independent of of choosing a certain prime? That's the question.
Not exactly. Don't worry about it.
Okay. Okay. No. Okay. The point is that the intuitive proof of the theorem. To prove it in, to give a complete detailed proof requires more work. I mean, there's technically is involved. Especially here, I assume that I'm defined over a number field, which is not in general the case, but that's the idea of the proof. Okay, so I still have some time, I guess. How much?
Maybe 10 minutes.
Okay.
Could I ask a quick question?
Yes.
Is this also some mixed Hodge theoretic invariant?
That's a good question. At the time, we did not have this in mind, but of course, now one knows we have several ways of knowing this, but I mean, it's not the best place to. I will maybe give a remark concerning mixture structure next time. Okay. So now maybe just a few minutes to explain why this theorem was a kind of failure for us. I mean, when we remarked when we remarked that from something, the point is that there is a conjecture which I don't have time to explain, and it's not concerned with my talk, but which was for Jan and me the main motivation at the time, is a so-called monodromy conjecture. The monodromy conjecture which we attribute to Iguza, even if I know no written statement by Iguza concerning the conjecture, is relates poles of Iguza p-adic zeta function. So if then its exponential is an eigenvalue of the monodromy. So I don't explain what is the monodromy, but the monodromy is something geometrical and topological associated to my polynomial f. So we were very happy when we could realize that by some limit process we can get something purely topological from the p-adic integral. So we thought, okay, now it's this z top that was written here is purely topological. So if the monodromy conjecture is true, it should be just obvious to relate it to monodromy. And so we were in big excitement at the time, and we thought it was just a few weeks' work to prove something like that, and at the moment it's still very much open. I mean, but it was a failure because we could not relate two objects defined over the complex numbers. I mean, before we could not relate object defined over p-adics with object defined over complex numbers. That's not so surprising, but okay. But nevertheless, we wrote this paper as to testify this approach. And of course, it was a challenge to get a proof staying within the complex numbers. And such a proof was obtained by using Motivic integration many years later.
Sorry, did you say you still don't have a proof of the monodromy conjecture?
Of course, yes. Of course, we don't have.
In the Archimedes case, none of the
Or in the Archimedes case, I mean, the conjecture comes from analogy with the Archimedean case where it's known. And it's very easy. In the Archimedean case, the poles of the corresponding integrals correspond to eigenvalues of the monodromy. That's known and quite easy. But the point is that this is based on integration by parts, and which is something you cannot do which has no meaning in the p-adic case. Okay. So now, more recently, there was some other you take x over c. So Calabi-Yau variety. So this is something simple. For us, it's something simple. It's just X is smooth proper. And you have a global form of dimension n, say. You have a global n form on X, number vanishing. This is very restrictive. For instance, you take the projective space. Of course, you don't have any global n form nowhere vanishing. Okay. So physicists, they have something called mirror symmetry, and this implies that two birationally equivalent Calabi-Yau varieties have same Hodge numbers. So that was predicted by physics. I think that nobody in algebraic geometry would ever guess such a statement. And in autumn of '95, but you have proved that if X and X prime are Calabi-Yau and they are birationally equivalent, then they have the same Betti number. With BI is just the rank of. So I took cohomology with compact support, but here they are compact. So the idea of the proof. So you take X with the global form omega and X prime with the global form omega prime. And you compute and by an easy argument, you get that if they are birationally equivalent, then the integral are the same. But in some sense, it follows from the change of variable formula. Almost, let's say, almost all P and all E. But this is expressed. This X is smooth for almost all P. So I do the same. I assume X defined over K number field. And also X prime. So this is essentially the same as the number of points of X modulo is the residue field. So with my previous notation. Almost all P. All E. So they have the same zeta function. The zeta function is just given by the Hasse-Weil zeta function is just given by these numbers of points. And here they are smooth and proper. So before it was I used the trace formula, but since I'm for smooth and proper varieties by the Weil conjectures, if you know the number of points in all the KPE, you get the Betti numbers. That's a rough outline of the proof. Okay, so you see it's somewhat similar to the other proof, but here, since we are dealing in the case where things are proper and smooth, we can deduce more from egality of number of points. We can deduce more. Now I will finish in 2 minutes. So you get only equality of Betti numbers. You don't get equality of Hodge numbers, which in fact I did not define yet. So this is a corollary of the conjecture, but not yet the conjecture. And so Batirev, when he found this proof, he explained it to Kontsevich, I think it was in October 95 or November at the IHS. And it was challenging to get a purely a non-p-adic proof, just staying over the complex numbers. And also a proof that could give a result for Hodge numbers. And so, shortly afterwards, Kontsevich solved this problem. And applied it to show that birationally equivalent Calabi-Yau varieties have some Hodge numbers. Okay. Then he explained this approach in talk at Orsay in December 95. And this gave us the impetus to develop, when I mean we, Jan and me, to develop further the theory. Okay, I stop here.
Question? I have one last question.
Yes?
Is there any way to use these techniques at all to prove rationality of Motivic function?
That's another. This problem of the rationality. There is. No, but I mean, maybe I mention this next time. But so Kontsevich introduced this Motivic as a veiled data function, and one is conjectured rationality would give another proof of the rationality of as a veiled data functions. So there is some issue here because there are counterexamples to some form of this conjecture, but if one modifies it in an appropriate way, I will mention this next time, it's still a conjecture. So, okay.
Any other questions? Okay, then we'll restart at 5.